All right. All right, we got that. What's up, everybody? It is Jason Watts. I am, yeah, so if you don't know me, my name's Jason. This is a little podcast that we do for, the just about Siemens automation. Today we're going to be talking about a little bit more of embedded systems talks and all of that stuff. But if you don't know who I am owner, CEO of a little company out of Alabama called Alpha Industrial Technologies. Got around 20 years or so of experience in industrial automation, most of it with Siemens. But yeah, so enough about me. Like, welcome to the stream if you're here. Not sure. Let's see. We got a couple people. Got a couple of people on. If you are in the stream and you're coming in, be sure to drop a like on it, and in order to get this out to more people, but then also leave a comment, join the chat. Today we're a little bit more laid back, a little bit less planned, but I tried to garner my I guess inner English professor look. I don't know. Drop in the chat like how well I get as like an English professor, maybe like Oxford or Cambridge or one of those places. Those are both in England, aren't they? I don't know. I'm from Alabama, so that's where I graduated. So I'm going to answer Brandon first. Yes. Yeah, so anyway, we are going to be talking. I don't know if anybody on here watched the last live stream last week. We were kind of talking about some pretty complex topics, and I tried to work my way up a little bit, but in the second hour, or I guess the second and third hour of the podcast, there was no really way of getting around the fact that you really needed to know a little bit about how computers worked. And I kind of realized that I'm sure that there's a lot of you that watch these that know that, but if you're new to automation, new to programming, you're kind of teaching yourself stuff, and you're kind of having to learn on your own. Maybe you're in a plant that doesn't have as much support, then maybe these are the first times you're hearing about like addressing and pointers and hex notation and all this stuff. So I realized that maybe it might be good to just kind of sit back and chat about some of the stuff that if you do go to a university or whatever, that you're kind of taught very early on in electrical engineering, because it's kind of the basis of everything. Even in a lot of like PLC and automation and that sort of stuff, you just take for granted the fact that like, oh, hey, you know what a hex number is, and if there's a number that's 4E, like that's one of those numbers that shows up a lot with like drives. What is exactly does that mean? What does that represent? And that's part of the thing that we're going to talk about today. Kind of have our first little setup here be really about the I'm just getting all my screens set up. If you've ever watched one of these live streams, you know how easily I can get distracted. So if this is your first time here, welcome. And if just kind of bear with me, sometimes I get a little cool off. It helps though with coffee today, not the monster. So yeah, so what I wanted to talk about today, if we get to it, I graduated from the University of Alabama, and I won't say what year, but it was not last year. But the class name that we took as I guess technically it was supposed to be a junior, so a third year university. I think I took it. Yeah, I took it as a third year. I actually changed majors. Just a little story. I actually changed majors from industrial engineering to electrical engineering in between my second and third year in college, because I realized that industrial engineering, while is cool and important, it's mainly like doesn't really have anything to do with like electronics and like making automation. It's more about like improving processes and planning projects and things. And if you know me in real life, you know that like those are kind of the like my weak points in life, like actually planning out projects and things like that. I can come up with the idea, but yeah, I like more executing. But anyway, the class that I took in it was called Digital Logic, and I'm gonna bring up this and see if we can kind of get a good overview of this. Let me move this down here, and we're gonna be talking about, I guess, just really like an intro to digital logic, which is kind of the basis of what all of our kind of programming and really how all of computers work. I'm going to mark where not to draw. Whatever, that works. So this concept and this first probably hour or so of this live stream is going to be pretty basic. So if you have a degree or you have experience in this, a lot of this stuff will be kind of like a review. And I'm not going to go too deep into the woods into it unless somebody asks like specific questions about it. And hey, Mario, how's it going? So if you have specific questions, like maybe something I'm talking about is not familiar, I will try to answer it. But I will be honest with you. This has been this digital logic class was, like I said, more than 1 year ago for me. And so some of these concepts just get used all the time. And so if something you have that you have a question about, it may not be on the top of my head, and I'm not afraid to tell you that I don't remember it or don't know something, but then I'll come back later and maybe do a short or something to answer your question. So let's kind of get started in on what digital logic is. So digital logic, and we'll call it 101. At Alabama, it was like 380 or something like that. I can't remember what it was. It was something like some 300 level class. But so the concept is that like all computers are 380. There we go. Yeah, so Brandon representing the U of A here. But yeah, the basic concept of all computers is the core is based off of a transistor, and a transistor is essentially just a light switch. That you have a light switch, a very fancy switch that can either be you have power, and it can either be off, in this case a 0, or in this case, well, that's totally the wrong case. It's the same case. In this case, it would be a 1. So in this up here, power cannot flow through. So over here, it's gonna be 0. Here, power goes through, so it's 1. That's the concept of digital logic. And this is a really simplified form of this, but yeah, so 1s and 0s. And we kind of talked about this last week when we got into the concept of hex numbers, because we were talking about, I was using notations that, and we won't go into it right now, but I was using like OX or 0x, and then there was a 16 pound like this. And if you're not familiar with different representations of numbers, then we're going to get into this. But this is a base 16 representation. Digital logic is a base 2. And so while this is 16, we have sometimes represented as 0B will be a base 2. We are normally in the realm of a base 10. So every digit has 10 possibilities. So base 10 is would be just like what we're used to. In each little space you have 0 to 9. So you have 10 different options for each digit. Well, in digital logic, because of this kind of situation we have here, we have 2 options. We either have a 0 or a 1. So if we start to build numbers, which not going to go into this now, we really need to go in later, but we start to build numbers, each space can only have 2 different options. That's why we have this. So what we can do is there's a couple of different math operations and stuff that we could do with these simple digital logic 0s and 1s, and we will start to kind of build up these topics into a full computer system. We won't do it here, but we'll get into kind of how the basics of it work. So the first thing of how these things work, if you have these inputs, you have kind of blocks and operations. Some of the core basic ones are the 2 most fundamental are the OR and the AND. And the reason why these are fundamental, and we're going to go into them even further, kind of like from a conceptual PLC standpoint, but this concepts of ORs and ANDs are everywhere in kind of logic in general and algorithms. Like even if you're writing in like a Python code, you're going to use an AND and an OR operations a lot. So the fundamental thing of a truth or digital logic is a thing called a truth table. So if you want to take an OR operation between 2 inputs, it will look, from a symbolic standpoint, you will have 2 different inputs coming in, input A, input B, and then on the output side, we'll call it Q. And the reason why I'll call it Q is because that's kind of the Siemens realm of it. And so an OR block has a symbol that has a little curved line here and does that. And there's a thing called a truth table. And so if we were to say, what are the different options for inputs A and B? Well, because of this kind of symbol over here, we know that each one of them can have a 0 or a 1. So you can have A be 0, B be 0, A be 0, B be 1, A be 1, B be 0, and then both of them 1. So those are all of the options for our inputs A and B. Wow, now this is called a truth table. And the reason it's called a truth table is because we want to see when our output is 1. And in logic, our output would be true at that. So when is our output going to be true? What combination of inputs based on what type of operation is going to have our output Q. So for an OR operation, think of it as if either A or B is true, then the output is true. Fairly simple. So if either one is true, our output will be true. And so the only one will be a 0. Pretty basic, pretty simple stuff. And this isn't like supremely groundbreaking stuff. But it's, again, fundamental to build up to these greater concepts. So an AND block is similar. We have A and B. Our symbol is a little bit different. Straight line. If I can draw, that's straight. And then Q. And its truth table on this side for 2 inputs is always the same. 0, 1, 0, 1, 0, 0, 1, 1. That's always the same. For an AND operation, it's the output will be true if A and B are true. So we can kind of go through here, and by that thing, the only time this will be true is here. Everything else does not meet that qualification. So fairly simple. Now, get a little sip. Again, if you have any questions at this point, fairly basic. You got a transistor, can either be on or off, and then you're creating kind of these logic devices and logic tables. And right now, none of this really ties together to anything. But what they end up doing later on is building up a structure that actually makes this logic. We're not going to go into that. We're just going to kind of get these concepts of like, oh, if you have a conversation with someone that's talking about this sort of stuff, here's kind of the basis of it. So let's go through and let's clear some of this. And let's go through and let's just recopy over here what we had. Just recopy over here what we had as this 0. Because again, ultimately, we could do this whole sort of thing in actual switches. Like in a PLC is a kind of modern version of what's called relay logic, because a physical relay, you can actually do ladder logic, the same concept with just relays. And if you go into an old plant, like there's a couple of steel mills in Alabama, or I guess metallurgical plants in Alabama that I've been into, that they still have processes that are being controlled by relay logic. And so they're actually using this sort of logic to make decisions of how to run their plant, and which is kind of wild. And it's all physical relays. It's no PLC, and it's crazy. And what's crazy is this, I mean, the transistor was like, what, invented in like the 60s? So all the way up until really like the 70s and 80s, it was all relay logic, which is insane. So getting off topic, but digital logic. So kind of the next thing that we'll talk about is we have this like we have what's called a NOT, and all it does is it takes one input, looks like this, and the output. So if the truth table for this, if A is 0, 1, it's just going to invert it. And that's fairly simple. So here's the thing about it. The NOT is really designated by the little dot there. And so what you can do is you can stack this not onto an or like that, and an and like this, and you will create. So this is an or, now it's a not. This is an and, now it's a NAND. And the truth table for these guys, so what you do, A, B, still the same, 0, 1, 0, 1, 0, 0, 1, 1. Now, normally, a regular output for an OR would be either or. So it would look like this. Well, for a not or a NOR, it's just the opposite. Fairly simple. This little symbol here, that's another designation for not. So if you see a bar over the top of an input or an output, it's not. Now, you can build up pretty complex circuits by taking and doing some interesting stuff to it, because this little block right here doesn't have to just stay there. It can be over here, it could be here, get all sorts of stuff. But we're going to talk just about that right now. So the NAND, in a similar fashion, A, B. So we'll do Q and then Q not, same way, just to kind of get the process. So B, 0, 1, 0, 1, 0, 0, 1, 1. So Q, both of them have to be an and, right? So either and or. So normally it would be like this. Right? Because they both have to be, it has to be A and B in order for it to be. So that's regular. So we take and we go 1, 1, 1, 0. Now, that's the core concept behind kind of logical operations. And the reason that we kind of go through this is if you really want to get into learning about logic, and we'll kind of tie those later like to the PLC concepts, but like when you're doing ladder logic, an and would be if you have a rung of logic that looks like this, and you would have your logic like this, would be A and B and then a coil. So this would be the equivalent of an and, right? So if you're used to PLC, if you're used to ladder logic, this kind of makes sense. A and B both have to be on in order for Q to turn on. Well, here is, if we can quick, see if we can get a little bit more. If we have this logic, we have this logic, oh, that is an OR, right? So, kind of same thing, same concept, same logic. And again, with a PLC, especially in ladder, it is based around these logical functions. It's based around logic. And so that's why like PLCs and then digital logic, they kind of get pretty close to each other. They kind of get tied pretty close in. So that's why we're talking about it. So same way, we put this little not symbol here, and then we added it to here. And essentially what we did is we added like this, right? So we've gone through and said a not, okay? So we've gone through and looked at this. And so if we were to kind of invert this, and in PLC there's like a NOT here that inverts it, you could get a NAND, and then if you could invert this by putting in this little NOT like that, you could get a NOR. All right, well, that's one way to do it. Or you can kind of do some kind of like logic with our truth tables, and it turns out that, remember I said that we could put these inputs, we could do this, right? We could put that little NOT on the input. Well, it turns out, let's look at the truth table for that. If we were to change the inputs of a NOT. So, or sorry, if we were to NOT both inputs of an OR. So A, B, normally it would be, our inputs would be, so if 0, 1, 0, 1, 0, 0, 1, 1, if we were to look at that, let's call it, hold on, let me, do the same thing that we did over here. Let's NOT our inputs. So B NOT would be 1, 0, 1, 0, 1, 1, 0, 0. And if this were an OR with both inputs knotted, it would look like 1, 1, 1, 0, right? Yeah, right? Which, oh my gosh, look, that truth table is the same as this truth table. So the actual, this right here. So a NAND must equal an OR like this. What does that have to do with anything, right? Okay, you're like, okay, cool, that's so useful. Well, if you take that same logic and bring it down here into the PLC world, guess what? If you, instead of having to do this NOT here, you could just do an OR and invert both inputs. So that's pretty cool. And that's a little bit, that's all we're going to do. There's a ton that you can go, and it's called reducing functions, by reducing logical operations. And you can cascade these things, really complicated. But if you want to start playing with those sorts of concepts, use these truth tables and use these kind of, those three blocks, the AND, the OR, and the NOT, and just start kind of playing around with them and write different combinations of truth tables. And you might discover things like an OR with the inputs knotted, so inverted, becomes a NAND. Things like that. Guess what? You might find a relationship between a NOR and the AND block. Probably the same thing. And so you don't have to have these sorts of you don't have to have these sorts of like output inversions, because you can change the way your code is structured and then invert the inputs like we did here. Anyway, so that is the core basic of digital logic. Now, next thing that I want to do, if you're still here, if you're still with us, is I want you to hit that like button. And if you haven't subscribed, hit the subscribe button. That's what I want you to do right now, because we're trying to get this channel out to more people so that they can kind of get more involved into this, and we start to build a community of automation engineers that are kind of working together. You have older, younger, because I realize that it's kind of random luck whether or not you actually get into a situation like in your first job to where you have someone that is kind of like a mentor. And so what we are trying to do with this channel is, even if you aren't currently at a position to where you have mentors that you can grow, that you can learn, you can get deeper understanding of the concepts, we want to be able to provide that. So by you liking all of the videos that you watch, liking the streams, commenting on the streams, that helps get us out there to more people. And then you are at the ground floor of that as well. And then as we start growing, you're growing with it, and then maybe you become the mentor one day. Maybe you are the old guy with gray in his mustache that sits and helps someone out with your experience. So yeah, like, subscribe, comment, all of that YouTube stuff. But let's get back to the next part of what I wanted to talk about, because we've been going for about 30 minutes now, and I started to talk about number representations before, and like we said, I'm just gonna go control. I'm not gonna go control A yet. I'm gonna do this and then hit control A and then delete everything. We're gonna start fresh, because we're gonna talk about number rep 3. That's an S. Representations. By the way, I kind of got, not really in trouble, but had an issue with apparently me registering some documents and things, and apparently my L's and C's kind of look the same if I get in a hurry. So yeah, I need to be more careful. Also, I don't know if y'all have noticed this, but my zeros apparently look like E's. Anyway, sorry for that. I have terrible handwriting. I think we all do. Press, like, if you have bad handwriting, raise your hand in chat for sure, because I think every engineer is required to have bad handwriting. Let me get my distraction device undistracting. Wow, that probably sounded terrible on anyway. So next thing we're going to talk about is number representations, and we kind of hinted at it, is that our kind of the 3 that we deal with as programmers in automation programming is binary, decimal. I don't know why I wrote it that way. I'm binary, decimal, and hexadecimal. So binary, decimal is what we're used to, and so like each digit, like if I wanted to write some random number, each digit here can either be, this can be 0 through 9, 0 through 9, 0 through 9, right? So that's what each digit is. So it is a base 10 number, a decade 10. going through all of that. That's what we as humans are used to. There's many other than these three. There's octal, for example, is a base 8 number. You have base 60 math that based on like Babylonian stuff and time and yeah, all of that. And stuff that's not used nearly as much. But for us, for the most part, what we're going to run into is these three: binary, decimal, and hexadecimal. We've known decimal all our life. So binary, each digit can be a 0 or a 1. So it can be 0 or 1, 0 or 1, 0 or 1. Okay. So that would be some number. So this is a base 2 number. Okay. In hexadecimal, each can be 0 through 16. Again, you may have already understand this, but we're just going back to basics. So 0 through 16. Well, our base 10 numbers, we only have 10 options. So that's where you get the letters from. So 0 through 9, and then you have A through F in order to get all the way up to 16. So, like 4, 1, A, E is a decimal, or sorry, a hexadecimal number, a hex number. And this is base 16. Now, converting between these, we can convert directly between base 16 and base 10. You can convert base 2 to base 10. Yeah, sure. But what we really want to do, because we're in this digital logic class, we're in digital logic world. Let's start by understanding kind of the between these two, and then I'll teach you a trick about base 16, because there's a relationship there that's kind of cool. So base 10 we all understand, so let's convert binary numbers to base 10 numbers like we're used to thinking about. So let's take a decimal 10. So this is a decimal number 10. It's a number after 9, right before 11, if you're counting integers, of course. I mean, we're not mathematicians, so we're not gonna be weird and talk about numbers that aren't integers. But let's convert this to binary, or base 2. So the way that you do this simply is you take your powers of 2, so 2 to the n, and you add them together. So the first spot can either be 0 or 1, right? The second spot represents 2. So if you put a 1 in the second, that's 2. And then you double it each one. So this is 1, double it, times 2, times 2, times 2, times 2. And so forth, and so on. So you just take and you're multiplying it times 2, just as you would here. So 2 to the 5 would be 2 times 2 times 2 times 2 times 2, 2 to the 5, right? And so that would be 2, or times 2, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. Yeah, right? So, yeah. So that's 2 to the n. Let's clear up some of this. And let's convert the decimal to decimal 10. So we're going to need at least 8, right? So we're going to need 8 plus 2 is 10, right? So there you go. And then all these leading zeros, because you can keep going, right? We're just going to forget about all the leading zeros. Just the same way, there's a ton of leading zeros on here, right? But we don't need those. Same concept. So this equals 10 in decimal. Pretty straightforward, pretty simple. You're just adding these places together. And you'll notice that the sum of everything previous, like this, if you add up 8 plus 4, 12, 14, 15 is always one less than the next place. Just kind of like getting stuff in your head. So like the most a 4-bit number can hold, it can hold the value 0 through 15. Because if you add all of these together, that's going to be 8 plus 4, 12 plus 2, 14 plus 1, 15. But that is 16 digits. 0 through 15 is 16 digits. And so that should clue you in to something that we're about to do. So practice some of that sort of stuff. We're not going to go into it very much here, but that's just basic binary. Is you're taking each place, you're multiplying it out, and then you're adding all the pieces together. Bigger binary numbers, the more bits, the more you can hold in a number. Just a couple of quick things. Clear off some of this. 1, 2, 3, 4, 5, 6, 7, 8. How many? If you have 8 bits, what do you get? A byte, right? So 8 bits in a byte. We talked about that last week. That's kind of our fundamental structure of what we have, just really in everything. Like the fundamental structure of a PLC, of memory, of words, that it's all based on bytes. So like a 2-byte word is a 16-bit word, because bytes are all, it is the core fundamental function, or the core kind of unit. Think about it. Like even on your like your hard drive, it's all megabytes, gigabytes, terabytes. It's all bytes, all powers of bytes. And so like that's 8 bits in a byte. So that's one thing to note, that as you start to go through memory, realize that everything's based not on like our tens system. It's based on binary. So how many bytes are in an actual kilobyte? It's not 1,000, it's actually 1024. And so I had a computer architecture class at the university with a beloved professor of mine. And when I was in grad school for a little while, he was my advisor. And yeah, Dr. Ricks, if you're watching this right now, hey, shout out to you. Because yeah, look, I'm not as messed up as you thought I was. But we had one class, and this is in a senior graduate level class, to where you have 4th, 5th year electrical engineering students and beyond, grad students, that were taking this computer architecture class. And Dr. Ricks got so mad after one of the tests. He was he started like, he was so mad because everybody's math, not everybody, but there were a lot of people that did their math. His question would be, say like, all right, I have one kilobyte of memory. and they would do the math based off of that 1 kilobyte was 1,000 bytes, and they would do their math, and the math was wrong. And so not only did he mark it wrong, he sat there and was like berating this class of seniors, and as he should, because this class right here, this might be the first time you ever heard of it, but this would probably been at least the 1,000th time that we went through these concepts as these 5th, 6th, 7th year university students, and he was so just like disappointed is probably a better thing that we didn't quite, that some of us not me of course, right? Some of the class didn't understand the fact that everything, even if it says kilobyte, a kilometer is 1,000 meters, but a kilobyte is not 1,000 bytes. It is 1024 bytes, because if you go through all of these base 2 numbers, that 1,000th place isn't actually 1,000. It's actually 1,024. So 2 kilobytes would be 2048. 4 kilobytes would be 4096. And so that little thing, yeah, just know when you're talking about memory, when you're talking about that, you're always talking about bits. Bytes are in terms of bits, and bits are always in base 2 numbers, never in decimal numbers. So just kind of a trick on that. Hopefully you're never working in such a memory restricted system that it really matters, but if you're working on like microcontrollers and you're doing like really complex, or trying to do things on like embedded systems, we're going to talk about kind of computer architecture that you may not actually have like that one little thought of like, oh hey, you're wasting a lot of space, you're wasting a lot of math, you're not doing your math right. And if you start doing, oh hey, my bits and bytes and stuff are off, like my shifts, you'll start shooting not to 1024, you shoot to 1,000. Now you're 24 bytes off, and your memory locations are who knows where they are. So that's why this is important. But so back to all that. So we've talked about how 8 bits in a byte, kind of hammered that home, hopefully. So what do you call four bits? If there's 8 bits in a byte, what do you call 4 bits? A nibble. Yeah, because I mean a full byte, it's a nibble, half a byte. Sounds like a joke, but it's not. Yeah, so 8 bits in a byte, 4 bits in a nibble. And there's a reason why a nibble would be important. Because if we were to actually go through these 4 bytes, or 4 bits, represent 0 to 15, or 16 total places, right? And I kind of highlighted this earlier. 16 is kind of an important number, right? It's that base 16 number here. So let's take this. This is 10. And so we could represent these 4 bits as the decimal of 10. And that would be a hex number A, right? And then if we had, say, a byte, and let's just throw some random bits in here. Let's look at this next little thing here. So let's just start adding. 1, 2, 4. So 5. 5 plus 8 is 13. So A, B, C, D. So this could be represented by D, because that equals 13, right? A, B, C, D. Yep, 3. 13. 10 is A. 13 that right? If that's wrong, yell at me in chat. Just boo me. But so now this big number here, which would be fairly kind of difficult to add up in binary, actually just comes out as a DA hex. So hex representation DA. That's what this big binary number is here. Now decimal, we would have to do that whole process. We would have to add together all of this. So 128 plus 64 plus 16 plus 8 plus 2 would equal whatever this number is. But if we use hexadecimal notation, we can break each digit down into 4 bits, which is very useful, okay? So when you see a hex number, so like if you're programming in a PLC, like if you're programming in Siemens, in a Siemens PLC, and you see a 16-pound 4E number, think instead of converting that into decimal, what is that decimal number? Don't ever convert a hex number into a decimal number unless it's some decimal number that makes sense. Most of the time when you're using a hex number, it's because it's a bit stream. It's actually better to think about it in bits, and hex gives you the easy way of breaking every hex number into 4 bits that at least my simple brain can easily process. So in this, our binary number from this 4E would be, so 1, 2, 4. Oops, I did that backwards. So 1, 2, 4. And then E, what is E? A, B, C, D, E. Okay, so that's everything, right? So that's 15. So that's everything. So 1, 2, 3, 4. Right? So what I'm doing with my hand is I'm counting, because A is 10, so 0. And then, so A, B, C, D, E. So 4. So that's all 4. Yeah, so 14. So it wouldn't be this one. It'd be that is better. So that 4E converts to this binary number here, which just so happens to be a byte. And it's so bytes are represented by 2 hex numbers, because you can split those hex numbers up into those. Kind of explore that on your own. If you got questions about it, like how to go through that, I'm going to show you an example here in a second of why that sort of thing there, because I didn't just pull that 4E out of the top of my head. That is an important number in getting a Siemens drive started. And we're going to talk about that. And we've talked about it before. I've actually brought that up. We've had a question in a live stream about that same thing. And this is the send telegram, this 4E. You have to send a drive of 4E and then a 4F, right? So you send a 4E, then you send a 4F. So this telegram, that first byte has to be 4E, 4F. So that's what that is. So let's go through now. And again, if you have questions about anything we're talking about on here and you're watching this on demand, be sure to drop a comment below about it. And yeah, I'll try to walk through it. We're coming up on about an hour. So what was the next thing that I wanted to talk about? I wanted to kind of talk about some of these basic instructions. So let's go in here. Let's do this. Control A. Say goodbye to all of the stuff. Bye stuff. Bye-bye. Yep, I'm insane. It's okay. So, next thing I wanted to talk about was real fast the concept of kind of our basic operations. OPERATIONS. So one thing about computer architecture is you may not be aware of how that processor actually works. How does your code actually run on the processor? And frankly, if you higher level languages get down and abstract away all the stuff that I'm going to be talking about, but it's good to understand kind of the fundamentals of what's going on in your processor. So what a processor, or what, I guess, let's talk about, if you write a program in, we won't talk about Python because it's something totally different. Let's talk about like a C++ program, okay? You write out your program. It is going to get, it will have a compiler. And you'll click the compile button. It'll go into the compiler, and the compiler will eventually spit out, call it assembly language. Which this may not exactly be 100% correct, but especially depending on your processor. But and then that code will get further brought down into what's called machine code. This is stuff like if stuff like this. That's what that logic looks like. Or that this code looks like that. This stuff looks like Phaeton. It's stuff like that looks like a it's terrible. It's terrible. I can't even remember some of this stuff. But yeah, this just looks like you'll have these like letters and then numbers, and then machine code takes it even further down, and it is literally just hex numbers. Like just blah blah blah. It's just literally a bunch of numbers. So your logic gets stepped through all of these different things. And again, great thing about your high level languages, and argue with me if you want and say that C++ is a high level language. It's a high level language to hardware people. If you're a software programmer, then C++ is like, it's not really a high level language. I get it. All right, whatever. It's just whatever. You can feel free to argue in the comments about it. Like, go ahead. But to a computer, assembly language and machine code are essentially the same thing. You have these instructions here that are one-to-one associated with your machine code instructions, whatever they are. Your high-level languages have a compiler that it's a separate piece of software that generates these breaks down whatever your instructions are over here into something that the code can actually use. That's what I say by high level stuff. But anyway, so that's how the whole process of you write code, it gets brought down, and eventually it gets brought into what's called machine code. And what determines what machine code is the instruction set of the processor. Now, we're not going to go too deep into it because you don't really need to know, because it gets all abstracted away when you're programming with something. But every processor wants to have fundamental instructions that can be executed on binary numbers. So some of these instructions might be like an add instructions. You want to add two numbers together. That's pretty important. You want to make an offset? You need an addition because you need to add one offset to another. Boop, and then do that. Have a subtract. You might have a load. Might have a retrieve. May have, if you're super fancy, which now you may have a multiply. You may have a divide. These are your core basic instructions. And all of these basic instructions would have what's called a machine code for that instruction. So this machine code, we might call it a 0-1. This might be a 0-2, and all of these are in hex representation, by the way. Remember, two hex numbers is 1 byte. 8 bits, you take 4 is 1, 4 is 1, 8 bits, byte. Remember that. So everything's based around the same. So your machine code looks something like this. Like these are like instructions. Whereas in assembly language, this is an A, this is an S, this is an L, call it an R, call it a M, you get where it's going, a D. So these just have assembly language instructions. And so you would want you would do something like load some value and then some location, which is like and then do like this would be like in assembly language instruction. Yes, Lucid, you're welcome for bringing this up. So Lucid brought up the fact that assembly language and STL are pretty much the same thing, and that's kind of why we bring this up, or that's why I brought this up, is if you're looking at an STL function on a Siemens PLC, guess what? It's essentially assembly language. So that's kind of, it is, you have these base level instructions that have assigned assembly language functions to it. And so that is literally all the only reason I wanted to bring this stuff up was what Lucid brought up, is that this is assembly and it also equals STL for a Siemens processor. Now, it used to be that this was the only thing that you had was STL, assembly language, because you were literally just working with the processor. If you were old enough to even have heard about what a punch card is, yeah, bless you, because you probably want to go, you probably have some like your medication that you need to pick up or you need a checkup for, you have a doctor's appointment that you need to go to this afternoon, because it's punch cards are originally the way that you would program, because you were programming in this machine code. And so you were literally punching holes in, like literally punching holes, creating binary numbers for each line of code. That's how they did it. That's how the code for like the lunar lander and all of that was like written, and all of those calculations were literally like hand punched out with a card. Yes. But so that is kind of what we're talking about here with our instruction sets for our basic parameters, and assembly language STL. That's kind of what those are. Not going to go into those because I'll be real, like Lucid said, it's traumatic. It wasn't my first program that I wrote. That was written in BASIC, which is, yeah. But the first kind of project I ever did, I was probably like in high school at some point, and I was messing around with like a PIC microcontroller. It had to be written in assembly language. And so, yeah, very traumatic. And I just noticed, by the way, I always do this. They're going to yell at me when my face is covering stuff up. Yeah, so assembly language equals STL on a Siemens processor. So that's kind of that. And one of the things that we kind of talked about last week is, get all over here, that we were talking about kind of like memory and how memory was allocated. And we kind of shift now that we've kind of talked about these hex numbers, and we have at least a basic understanding of what they represent, and the fact that that some of these numbers, let me get my bearings here so I don't mark it. So some of these numbers that we are looking at represent not just, there's a little bit more meaning to it. It's not just like a decimal number, some random number. So like, for example, we talked about last week how if you have a block of memory, it is going to be broken up into essentially, well, bytes. For the most part, it's going to be bytes. And we'll just use bytes because it's a little bit easier, and because most of our pointers that we talked about last week were originally set up for byte level access. So we're going to call this byte 1, byte 2, so forth and so on. Well, each location would be called byte 1. So this would be, we'll call it, except we're going to start at 0, 1, and so forth. Before I do that, so this is going to be 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 5, 6, 7, 8, 9, A, B, E. So we're doing this. So these are these numbers over here are the actual, call it, that's weird. Oh. Call it, we'll call these our actual address. So we talked about this, or this could be so yeah, this is going to be our address. Now, what is inside of them is going to be 8 bits in these bytes. So these numbers do not have to aren't going to be. So this could be 4E, 1, 12, A7, blah, blah. So this is the actual data. So what's in red here is the data. And those are two different things. So the address and the data, they might be the same, probably not. Because the address represents where it is in the physical memory. Because your physical memory is just a set of what are called registers. And in the computer architecture world, those registers have an address. And then each little point as you're going down through contains data and some extra stuff to be able to how to actually address it. So it'll have an address and a data. And we're not really going to go too much into this, but the size of your address means how much you can actually store. So it wasn't too long ago that 64-bit processors were not really what's it called? They weren't really available to the common user. So like most everything was 32-bit. Well, that limited your what's called your addressable memory space to a little over 3 gig of space. So you had to start doing tricks in order to address anything over 3 gigs. So that's why you could only have so much memory. You could only have 4 gig of memory because of this address only being able to be 32 bits. And once it went up to 64 bits, that's when all of a sudden your processors can address your memory that's greater than that 4 gigabyte range. And again, the usable memory space was less than 4 gig. So until you went up to 64 gig, you couldn't really use more than 4 gig of memory. You had to have a 64-bit system. So all you people that have never, I'll call you kids, but like, come on, y'all are the next generation. But I was just talking last night with someone just about the fact that like it wasn't like in my lifetime, in this century almost, that the yes, Lucid. So that is why earlier could only do integer math, because you only had 16 bits, because you had 16-bit processors. You couldn't do floating point operations. I mean, your word size had to go down, because in order to, you can still have a float on a 16-bit processor, but the size that it can contain isn't necessarily or it's definitely not the same as going from a 16-bit word to a 32-bit word. One of the other things that we kind of talked about previously is that instruction there, if there is not a floating point operation multiplier in the instruction set, floating point math takes a lot of time. And so more specifically, the answer to your question, Lucid, about earlier processors could only do integer math is because they didn't have a float multiplier, or they didn't have a float subtractor, because that's kind of a totally different operation when you're working with the bits and the bits in the word. But yeah, so that goes back to kind of like what's actually built into the hardware. Now, sure, until you get to 32-bit processors, it gets a lot easier to do that sort of math, because you're not having to juggle different integers, and like, yeah, it was a pain, and it was like technically expensive, but also back before the actual, so imagine you only have so much space that you can physically work with on a processor, because you have all these transistors that make up all of these logic things. Well, you can either make your processor bigger, or if you want to add in more stuff, you can make transistors smaller. And so that's kind of what processor technology has done over all of the years, is make transistors smaller so you can put more stuff in that space. Well, once transistors got small enough to where, all right, we have this space to add in these extra instructions, it becomes less costly to actually take up the physical space to make a float multiplier. So like float multiply, in order to do it very efficiently, you would need to have its own specific little area of this chip. And so it's like buying a downtown New York City real estate, very expensive, so it better be worth it. So that's the biggest thing with the older processors, more so than kind of the bit structure. It just made it even more expensive. So back to this kind of like addressing. We talked last week about pointers, and kind of the core way a processor kind of works is it has this space, call this like our memory space, but then call this memory. Okay, well, you have this other space that's called the program space. Okay, and it's the same thing. All it has is a bunch of addresses and data. So it's addresses and data. Well, what your code does is, in layman's terms, it says, all right, start at in the program space, do this instruction, then this instruction, then so forth and so on. So it's literally just a list of instructions. It's a list of these machine code instructions that we had before. And so ultimately your program gets compiled down to, remember we talked about just a second ago about these different machine codes that just like an add might be like an add equals 01, a subtract equals 02, right? So it's taking in the data, say you want to add, and then a load is an 03. Let's do that. Let's say we want to load numbers. So we want to load, and then this next one would be the data, and then address. Or actually, that's not how that would work. It would be, there's a specific space. So it would be a load data, and then we want to do another load data, but it might, so this might be load 1 and then load 2. That's, and then so this would be a 4. So what would actually be in here, and then that's going to be data, and then we would execute a 1. Okay, so that program, starts here, and just bumps, and just does each machine code operation. This is not a little bit abstracted, but it's basically what it's doing. And so it just kind of bumps down through each one of these little sets of I think I can just do this. So it's just going like this right here. All right. Well, these are, yeah. So these have the same 01, 02, same addresses like we have over here. It has, and so that's just it. Okay. Well, we talked about pointers last week, and what actually we talked about a pointer essentially being an arrow. Okay? And there's the most important pointer of them all is what's called the program pointer. The program pointer. And all it does is contain the address of the next instruction. So you have a program pointer that is saying when you start off your program, it starts at the beginning of your address space and then starts stepping along. And that's what this is. And all it is just a place of memory. It might be right here. Okay? So it just, and all that does is holds the address in the program memory of it. So that's all a program pointer is. That's all a pointer is. Just remember, a pointer is essentially pointing to an address where something important is. It's just an arrow pointing at an address. In this case, it's pointing to the program. That's a program pointer. And where it resides kind of doesn't matter, but I mean, it does, but like to you, it doesn't. But in essence, every time that you go from one instruction to the next, you're incrementing that program pointer. The reason I wanted to bring this up is because every processor, including a Siemens PLC processor, including Allen Bradley's processor, including a PIC processor, an Atmel processor, like whatever processor you're using, they all have program pointers, and they all have program memory. They all have load memory. They all have random access memory, RAM, the memory that's available for you to kind of shove stuff into different places. So the reason I bring that up is because I wanted to talk about kind of the core basics of how a PLC memory structure works, because I've talked about many times on here in memory and inputs and outputs and data blocks and all sorts of stuff like that. Well, PLCs have less or more restricted resources than your kind of desktop would be. A PLC might have a few megabytes of program memory, whereas technically your program memory on a processor on your is only limited really by not even the RAM. But yeah, RAM essentially. So if you have 64 gigabytes of RAM, then you can write a program that you wrote it that long, like, bless you. But yeah, you could write 64 gig of program and it all get loaded in, and even then there's ways around getting around that restriction. And so yeah, there's all sorts of stuff that's in that high level stuff. But just know that in a Siemens or in any PLC, you're going to have this kind of restriction in kind of the what you can use and how much memory you can use. The way a Siemens, and really most processors, I don't know of any other processor that's not this way, but in a PLC or in a processor, you have your physical I/O. Okay, and like if you've ever used an Arduino or PIC processor or anything like that, you're actually interfacing in with a physical I/O. And so this could be like a digital input, digital outputs, analog inputs, analog outputs, relay outputs, whatever. RQ, like all this stuff. So this is like the physical interface into the world, right? And this sort of stuff has its own processors, because like this IO has to interface in somehow. So like the PLC itself, doesn't have like an input pin per se that is going out, and when you hook up your input into your rack, it's not directly tying back to your PLC somehow. It's not doing that. What it's doing is it's tying into, think about it like an Arduino or a PIC, it's into a microcontroller there that then communicates to your PLC somehow. And this is the actual hardware. So that's like an actual processor that is interfacing into that physical wire. Like that. Here, that then goes into a place called your... Ooh, that was rough. Process image table. Okay. And your process image table takes, and it's just a place of memory. Remember, when we're talking about memory, it's just a bunch of addresses that store data. In this case, the process image table takes and communicates with all of that hardware in some shape, form, or fashion. Doesn't matter to you right now. And it brings in copies of all of this data. So there is a process in between here. How did that not turn over? There we go. There is a process in here that goes out and updates all of each one of these individual things here. Okay? That's the process image update. So like that is a process that you don't mess with. You can configure it if you like getting yourself in trouble or if there's some specific reason. Like sometimes you need a very specific analog updated faster than normal. That's where you would go in and change that sort of stuff. Very advanced stuff. Don't worry about that. That's mostly taken care of for you 99.9999% of the time. Now, so you have this process image table, and what you also have is, just like any processor, you have your program memory. Okay. And that's where your code it sits. So this has FCs, FBs, OBs, OB1, blah, 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 all that stuff. So that's your program memory. There's also there's load memory. Now, I tried to write it to where load memory was bigger, but your program memory has an interface between the process image table, and it goes, and program memory never touches the hardware. It never touches it. There's this other process that works. It only interfaces in with the process image table. That's to protect you from all sorts of stuff. But so your program only has access to the process image table, and there's a limited connection back here. We'll put an asterisk on that because your program memory in real time can go back and forth between load memory, but it's not really recommended because this is on like a flash card. So your little flash memory card that you put into it, your MMC, that's in flash. So there's a limited number of read and write cycles on that. This is in RAM. So is this. So that memory is designed to be constantly, forever, written and read and written from. Like, so that's this little section. All of this section is in RAM, and then this section would be in flash. So I'll kind of draw it out like this, like that. So that's the basic structure that you have in really any PLC. There might be a little bit differences on some of the stuff that's just kind of dependent on that processor, but this is your core principle. In your flash memory, you can load all sorts of stuff into it, and then there's different functions and stuff that you can kind of like grab that stuff out of. But that's where, if you're running into like really big recipes, this space over here, so like this space is limited, whereas over here this can be it's like really huge space over here. And so you might want to take, and if you have like half of this space stored up, you would never want to load all of this over into your program memory, because it's just a waste. And so you want to create one recipe, and then at some point when you load it, it goes and gets that recipe out of here and loads it into there. And that's what kind of pointers and stuff really, really help with, is because you can just point over into load memory, create an offset, point over into load memory, and then bring it over. And yeah, you could get in trouble doing that, because you could literally, because part of this is this load memory, this flash memory, has your program. Okay, so it has your program in here, and on startup, it takes your program and transfers it over. And then startup, your process image table gets updated from everything the first time through. So if you kill this flash card, you could kill everything. So yeah, that's a mess. But so that's really, unless there's any other kind of questions about PLC memory, we're about an hour and a half in, and I was going to kind of spend some extra time talking about some actual Siemens PLC or Siemens drive stuff, because I mean, we all know here, this is, I play around and act like that I want to work with PLCs, but we all know that the only reason we work with PLCs is so that they can control our drives, right? We're drives people at heart. And so unless there's like questions about like some sort of memory topics, and if we're going along and you come up again, always ask questions. If you're just coming in on the stream, I noticed we've had a couple of people come in, probably on your lunch break. Yeah, like, if this is your first time here, always like, actually everybody, if you haven't already, like the stream, because that's the best way to get everything out. We always talk about, or I always talk about the algorithm, and until you've done YouTube videos, you don't understand the importance of the liking and commenting on videos. So if you would, please do that. Even if you don't subscribe, like, please just like and comment if you would. But yeah, if you like it though, why not subscribe? So here's what I want to talk about for hopefully the next little while. I want to talk about a little drive that is called the V90. And in the US, if you're here on the US, you probably have never heard of the V90, because it is, I think Siemens calls it an emerging market product line. Basically, it's a lower cost drive that they made in order to really access the Chinese market. And one rule, if you don't know this about like Chinese market, is they have a lot of restrictions on what Chinese companies can use in their plants. And so one of those restrictions is having the equipment being made in China. Like, in a lot of cases that's the thing. So this is made in China for really the Chinese market, but because it's a less expensive drive just on its core, it's used a lot in simple applications. Now, in the US, this drive is not really, it's not as attractive because the feature set of the V90 is more limited compared to some, like, I believe the S210 is a single axis lower performance version for servo motors. It's basically the same thing, but it has more features and it's more expensive. Well, I guess it was back in 2000 and, was it 18? Yeah, it had to have been, because President Trump enacted a bunch of tariffs on Chinese products, and well, the cost effectiveness for us American programmers aren't there, because overnight the price of these drives went up by 25% because of a tariff. So if you're not in the US, these drives are really a good offering for if you have a small or simple project. The drives, I don't know what the exact kilowatt range are, but they're around, I think they're all less than 2 kilowatts on the motors, but they're a servo drive, have built-in feedback. They use the 1FL6 motor, which is a really good motor. And yeah, they have Profinet communication and all of this, but yeah, what we're going to do is, I'm going to flip this over to last screen. Yeah, here. Yeah. So what we have here, we have a program called V-Assistant, and that is the B series software package. And I'm going to show you a little bit about just simply setting up, I'll do an offline. I wanted to set one up offline. There we go. So if you wanted to set up just one offline, you open up V-Assistant, and for V-Assistant, it's in this version, it's targeted for the V90. And I will say that I have a couple of products and a couple of projects that I've done out there that the first ones I did were in like probably 2017, somewhere around there. That's when I ordered them, and then 2018 comes around, and then everything changes. So I actually have projects out there using the V90, and so we're just going to do an offline configuration. We're just going to do a new project, and as we can see here, it goes up to 2 kW. Doesn't really, so that's on the 200 volt. So let's do 400 volt. Oh, wow, look at that. I'm wrong all the time. So with the 400 volt, 480 volt, these are good on 480 volts, by the way. You go up to 7 kW on that motor. And the reason they're paired, so the drive and the motor are paired together. So let's just do this 0.75 here, because that's actually what I have that I've worked with before. And shows you a little picture of the drive and the motor. And what you'll see here is a very streamlined, very straightforward package to set these things up. You essentially go through and set up, you choose, do you want it speed control, or do you want to use what's called Epos, the basic positioner, the electronic positioner, or I'm sure that it's some sort of like German. If you know what the German representation for Epos is, put that in chat. But when I first started using it on the master drives, I always called it my dad called it the easy positioner because it's so easy. But yeah, so all you do, pick speed control or position control, basically. And we're gonna do basic position. So speed control, pretty simple. It's running in speed control. You send it a speed set point, and it's a Telegram 1. But for the basic positioner, what the basic positioner is actually a built-in position control function. So all you're doing is you're sending your drive a position set point, velocity set points, and all of that data, and it actually controls the positioning functions built into the drive. And it's actually pretty high performance. It's pretty good, and the fact that it is built into this little V90 makes it to where you can do some pretty cool projects. Project that I have this on is actually a fully automated bandsaw, and it's doing all sorts of positioning. It's positioning a tumbler, it's positioning things in order to cut teeth in a ring, and it's cutting out different rings. So it has a up and down bandsaw, it has a positioning rotating, and it has to shift back and forth in order to make these like straight teeth out of this round cutout. But that's all done on the drive. So I send it like a degree set point and say go, and it goes to the next one, go, next one, go, next one. And that's using the Epos. I just wanted to show just a couple of things about from the drive side in vAssistant, and then we're going to shift over and kind of talk about how to understand a little bit more about this Epos functionality, because it's not really shown very well in vAssistant, but I'll show you a trick. One thing about Epos is it's always going to be Siemens Telegram 111. 111 is the Epos Telegram. So if you are using Epos, you are using 111. So what we have here, obviously, Siemens Telegram 111. We can give it a supplementary telegram if we want to. We're not going to. We have our network configuration, IP address of the of this station. So the drive itself. This is the IP address of the drive, and name it. So if we wanted to name this, we would want to call it something drive. Remember, the underscore, I'm actually hitting underscore right now. It's an illegal character. Don't ask me why this is this way, but in Portal, the default name for a drive has an underscore in it. Come on, Siemens. An underscore is an illegal character. And so if you ever have noticed this in Portal, it goes drive_1. And then if you look at it, it says converted name of the IP address, or the converted Profinet name. And it has some like drive XA121. It's some weird name. I don't get it. If anyone could tell me what the reasoning was, please tell me so that I could stop being in it. Because all you have to do is just use a dash instead of an underscore. And that's a legal Profinet name. The underscore is an illegal Profinet character. Anyway, rant over. Then we go back and we put in our IP address. So like 192.168.0.10, whatever. Cool. Put in a subnet. Don't have to have that. And if we were online, we would be able to save and activate. And so if you notice on this screen, you have on the left-hand side is the program set. So your program set, and then further over is on the right-hand side of the screen is going to be your the active name. Since we're not online, it's not active. So parameter, set those in order to get that, and take a note that this network configuration, mainly the communication between the PLC and the drive is only activated after a power cycle. So remember, before you power cycle, you got to copy RAM to ROM and then power cycle. But yeah, we're gonna do that. So just know that's where you set. Here's kind of the parameterization that you're looking at, and I won't go too deep into this, but I guess I probably do need to go a little bit deep into it. Let me move it down onto here so I can kind of talk about this, because Epos, this is probably the most important thing in an Epos, is getting this set up correctly. Oh, that is totally the wrong thing. I want that, and I want to move me over here like that. So, what we have is our gear ratio is the first thing that we have here. All right. And this is, again, like I said, this is probably going to be the most important thing if you're using Epos. And if you've ever used Epos, you're screaming, yeah, if you get either of these things messed up, it messes up everything. So don't do any programming until you fully understand what's going on here. Say again, don't do any programming, because if you change this number, all the numbers in your PLC program will change. If you change this, all the speeds that you're actually physically running at will change. So yeah, just please get this set right. What this is your total gearbox factor. Okay, so this is your total gear ratio. Okay, so this ratio is on your motor revolutions. You can have a gearbox, a pulley, so like pulley reduction, then a slide, like a rack and pinion reduction. You can have all of these reductions. You have to group them together to say how many motor revolutions equals one what's called load revolution. Now, in a rotary axis, this kind of makes sense, but we got to talk about what in the world Where is it? Where is it? Where is it? Where is it? What in the world is a LU? What is an LU? It's the most critical concept of using Epos is to fully understand what an LU is. So I'm going to clear this out. We know now that this is just this total gear ratio, but we're trying to figure out what is a load unit and what is a load revolution, because that's the most important thing that we have here. So let's clear this out and talk about what a load revolution is. And I'm going to keep it on this little screen here. I'm going to move me down to here. Yep. I'm going to move me down here, and we're going to talk about what is a load unit. So, or sorry, a length unit, because it's kind of easy to think about in if we're talking about, oh yeah, so apparently there's a good channel. So Electrical Automation Hands-On channel made a whole playlist explaining these details. So yeah, so there's definitely other resources out there too to explain this as well. So what a LU is equal to a length, a load unit, but for right now, because we're working in a linear axis, LENGTH, length unit, that is how we're going to think about it. Okay, so if we are in a linear axis and we want essentially to be able to talk in hundreds of what's it called? That is a meter. Okay, and we're wanting everything's in meters, millimeters, something like that. We want everything to be in a millimeter. Okay, if that's our, or maybe we want it in 1/10 of a millimeter. And so this is kind of like the length unit that we are getting into. And so what we want is we get to pick what this length unit is. So if we want it in millimeters or 0.1 millimeters, we get to pick it. We get to say, all right, our process is going to move along this line, and it's going to move in this direction is positive, and it's going to move in millimeters. So that's what we want. We get to pick that. And what happens is we want to have this ratio is between 1 motor revolution to 1 length of our overall product. So what is the ratio between motor revolutions to the load? And then 1 revolution of our load, what that ratio is how much resolution. So in this case, we have a 10,000 length unit revolution. And it's kind of easier to think about this if we're thinking about it in a rotary setup. So I'm gonna go through here and flip this over to a modular. I don't know why it's called a modular. It's a rotary axis with a modular range. That's a confusing thing. So let's think about it from the standpoint of of just a simple gear ratio. So if our load unit equals degrees, okay, and we have a 2-to-1 gearbox ratio, that means the motor will have to go 2 times for every 1 rotation on that. So our motor would rotate twice. Our 1 rotation of our load, it would be 2 to 1 that way. Now this length unit here, 10,000 doesn't really make sense on a rotary axis if we're wanting it in degrees, because we all know that 360 degrees is in 1 revolution. Well, if we wanted this in our resolution to be 360 degrees, 1 degree increments, then we would put 360 degrees. So we have our ratio. We would put 2 to 1 here, 2 motor revolutions to 1 output, so it's geared down. And then we would put 360 degrees. Now, word of advice. This is not nearly enough resolution. You could be like, oh, well, I'm never going to want tenths of degrees or hundreds of degrees or thousands of degrees. Why in the world would I want that? Well, because when you start doing your math later on, you're not going to have enough numbers to work your speed. Like your velocity is going to be in per second, and then per second squared will be your acceleration. So those numbers, if you don't have a big enough number to start with, if you don't have enough resolution, then you're not going to have enough resolution in order to actually get good values on your numbers. If you only have one value a resolution of 1 degree for our setup here, the slowest you would be able to run would be 1 degree per second. And you're like, okay, well, I would never want to run slower than 1 degree per second. Okay. You're like, all right, that's fine. Well, you might find that 1 degree per second is actually too fast, and you want to actually run a little bit slower for whatever reason. And this is especially like when you get into these oddball length unit, like the revolutions per load. So my suggestion is always give yourself at least like 100 times, if not 1,000 times there. Because the motor encoders are so accurate that there's not really any reason for you not to do this sort of thing. And there's a couple of other things in Starter that will actually show you when you're setting it up, if you're doing this on another drive and you're using like this on an S120 or even a G120. In Starter, it'll tell you your minimum resolution, and you can see that it kind of doesn't work right. One of the other things is, if you have a high gear ratio here, say it's like a 50 to 1, then your load revolution, in order to get fine resolution on it, it's having to make really big changes with the motor speed, and you don't necessarily want that. You want to be able to have that finely tuned, adjusted load. So always give it more than you think you should. At least 2 zeros. So whatever you come up with here, put 2 zeros on it, and you're probably going to be okay. Again, if you don't get this right and you set that wrong, all of your math, and then you go in later to say, oh, hey, this doesn't really control that well. Like I've set this number wrong. Well, when you go back through and change it here, your program isn't going to work. You'd have to go back through and change all of your set point variables and all your conversion factors and everything on your PLC. So make sure you do this right. I dropped my pen. So let's clear this out and go. So the next couple of parameters that we have here, let me move me back over to here. So we're not going to talk about this. This is called the traversing table. We're not going to do that. So the ramp function module is one thing to think of, to know about. Now normally you're going to want to have as fast as a response as possible. And so by default, there is no ramp function generated when you're using Epos. So like if you do like a jog, there's it's pretty much just like as fast as it can go. So like if you're accelerating according to like your function in your Epos, it's going to accelerate that fast no matter what you put in there, and that could get you in trouble. But here's an option to be able to configure a ramp function. And the thing about it is, I don't even know if there's a function in Epos, because when you enable Epos, it's a position controlled move. Just like the technology objects use the position control, they all are inherently position controlled. You can control acceleration and deceleration in Epos. It's just not controlled with a ramp. It's controlled with an actual acceleration factor. So like linked units per second squared. So let's look at this. So these are limits on the torque limits. And yeah, these are basically, you can kind of go through here. Here's the configure the referencing. So if you are going to do an absolute move using the Epos, the axis has to be homed. Now, most of the values that are on in these 1FL6 motors, or sorry, most of the motors, you're probably going to have an absolute encoder on them, and you're just going to select it's not going to be that. There is a place to where you can set it. And maybe I missed it, but anyway, there's a place to where you just set the reference on that on your absolute motor. But otherwise, this is very similar to the homing function that I've talked about in the technology objects. When you execute these functions, it's going to actually move through this kind of profile. And again, if you notice, all of these values are in linked units per minute, and your accelerations are going to be in linked units. Your total distances are going to be in linked units. So again, all of this goes back to knowing what your actual mechanical system is set to. So that is your that kind of basic parameters, basic setup on that. Commissioning, if you're using a V90, there's a little optimization, and I think it's one button auto tuning here. You can online, you can go through and actually turn this on, and this needs to be connected up to the system, because it's actually going to go through and see the response from the physical system. And you click that, and here's the dynamic factor. This is something that I'd just play around with before you're hooking it up to something that's super important, because these dynamic factors can be really dynamic and they can catch you off guard sometimes. But just make sure that you're not doing anything, that you're clear of it. You're not sticking your hand in somewhere while you're doing this that might injure you. All that to say, I want to go out of vAssistant now, because that's really basically all it is going through and selecting the drive, selecting Epos, and then downloading. And there is a button if you were online right here. Remember, on a Siemens drive, you have to copy RAM to ROM. Otherwise, it comes back with your old program. You work for a while. If you like what you have, you copy RAM to ROM, okay? And that button is right here, save parameters to ROM. That is what you're going to do. It's only available when it's online, and you go from there. And then you can just save your project, do that. So we're going to close out. I'm going to close out. Go back, close this out. I'm going to get starter pulled up. And the reason I'm going to pull up starter is because it has nice little graphics for Epos. When TIA Portal was made, it kind of was built around this technology object portion. And so what I'm gonna do is I'm gonna show you if we are using on an axis. So project, well, let me get you actually over onto something here. Go back to my sketchpad. We're gonna do like a project new, and we're gonna do and we're gonna insert single drive unit. We're gonna call it, let's do a, we're gonna do this on a yeah, I'm gonna do it on this because C320-2 PN. Yeah, that's all fine. We'll just click through, configure a drive, because this is what we want. So when you're configuring the drive, you have to set this up, this technology. Well, I guess we don't do it here. So we're gonna set this up, and then here is where we go through the basic setup. We want to select basic positioner. All right, otherwise none of these options are going to be showing up. So and then we're just going to kind of blow through here in order to get to our stuff. None of this part really matters. We're going to set this again. I'm just wanting to explain about the Epos, and because we selected that Epos, it is going to have a couple of different options here. And so here is where it says what encoder is going to be used for position control. And so there we've got that. I'll show you where we can change this here in a second. One other thing about it is we want, right, Epos is Siemens Telegram 111. We definitely want Siemens Telegram 111. And if you notice, we don't have a bunch of other stuff. Like Epos is only available with certain telegrams. So we're gonna go back through, and now we're gonna go to Axis, Functions, nope, Technology, Basic Positioner, not Functions. And then we're going to, well, I'll show you first. If you're using Epos in starter, be sure to go to the mechanics screen first. Remember, I went ad nauseum about getting your linked unit set up. Here is where you set up your linked units on this in starter. Same thing, get all of these things set up right. But what I want to do is go through and explain to you the different functions that are available in Epos. So Lucid asked a question, do you have to buy a license to make the Epos available in the V90? No, you absolutely, on a V90, it is available for free. But the G120, if you're using a CU250S, it requires a license to activate Epos for the G120, but not on the V90, because V90 is inherently a servo drive, whereas the G120 is if you're doing positioning with a G120, then you're doing some kind of out of the ordinary stuff with the G120. But obviously you can definitely do it. It's just not normally what it's used for, whereas that's what the V90 is for. So let's So all this stuff here. One thing I will point out, I didn't talk about it. This is in V90 as well. The backlash correction. Once you figure out how much one length unit is, so if you know that one rotation or 10, like through your gear rotation, one rotation of your motor equals 0.1 inches or whatever, and then that's 1,000 length units, then you know that one length unit equals 1/10,000th of an inch. Okay, well, this backlash correction here, if you have a gear ratio or some sort of anytime that you change direction on an axis, if you don't have some sort of backlash correction, you'll get creep. And so if you have like a standard gearbox or kind of like an old rack and pinion setup, and there's a little bit of play, every time that you take up that backlash, it's going to be pushing like this. It'll be moving in one direction, and then when you go to reverse it, the motor is going to move back in the other direction, but the gear itself is not going to move. So your load is not going to move. And so every time you reverse direction, you're going to induce whatever your backlash is. You're going to induce an error into your overall performance. So if that backlash is, say, 30 length units of backlash, then every time you reverse your motor, your end result is going to be 30 length units wrong. And so that's one thing to know, is that once you get your system set up, put your length units in there into the backlash correction, and this system will work a whole lot better. And all that's doing is essentially going, every time it reverses direction, if you have 30 length units of correction, it's going to add 30 length units to the overall set point. So if you have a 1,000 set point, 1,000 length unit move that you're doing, the actual move that'll get loaded into the Epos will be 1,030 because of this backlash correction, because it needs to move 30 length units first before it even starts to move. Makes sense? Hopefully. But yeah, so we're going to talk about, that's the mechanics. That was mechanics. Couple of things that you have Epos. You have your range limitation. You have hard stops and soft stops. So your negative impositions, so your software output cam activation, or sorry, your software in stops need to be outside of your hardware in stops in theory, right? So if you lose your actual input here, which can be like a digital input, so like if you hit this software in stop, this output in stop, it actually faults. Whereas this unit here, I don't know why I'm using my mouse instead of just, so these equal fault. These makes it to where you can only opposite direction. Opposite. I spell. So if you have, say for example, this here, and you're moving in the negative direction and it hits this, it won't allow you to move negative, but it will allow you to come off. Like negative will get removed, but positive would be okay. So that's what these end stops are, and that's built into the Epos. Let's see, traversing profile limitation. So these are your actual like velocity, acceleration, and jerk. And these sometimes, remember, this is where I was getting into, these values only make sense if you really understand what your length units per revolution are, like your load units are. So yeah, so that's basically what that is. What I really wanted to get into was what's called MDI, and here it's called direct set point specification. Yeah. What is it? What is MDI? I'm sure that's German for something, right? But we're going to talk about all of the signals and everything that are on here, because these signals here come from, you notice, these are all signals in the PZDs. So these are all Profi drive. So these are control. Hold up. So all these are control. Okay. And so what you have to do in order to get these things to work, what MDI does is you are giving it a set point, essentially and you kind of see it here. You're giving it a position set point. You're sending in a position set point, and then it and some other parameters, and it's going to accelerate up to a velocity and then decelerate down, and that is going to be your position set point. And so you can kind of see this here. That's what that is. So PLC sends the position set point, the drive takes care of it, and then these are your control words. So let's see, you got to have these 2 bits have to be on. So let's talk about each individual bit. So MDI selection, you have to have this on in order for this block to run. This has to be on for this block to run. Pretty straightforward. So you probably will not use the setting up selection. You're not even really going to talk about it because it disables some stuff that you probably wouldn't want to do. These 2 things are kind of like your e-stops and a pause. So let's talk about it. You have this bit here is called your reject traversing task. Reject traversing task. You're just rejecting it. Think of this is kind of equal to an e-stop. Okay? So it's kind of equal to an e-stop. It's not an e-stop. But it serves kind of the same thing. It kills the motion. You got to refire it. Whatever it's doing, it stops it. And honestly, here's one thing though. If this is on and this is not on, you will get a warning. You will get a warning, an alarm called reject traversing task missing. Okay? If it was in the middle of a move and you withdraw this, you will get a fault. It'll say reject traversing task withdrawn while traversing. So it'll get a fault. So if this does not, you have to turn this on in order for anything to work. Okay? You have to turn on your MDI first. Then you have to turn these two signals, the intermediate stop and the reject reversing task, on first. Both of those have to be on, and then you can trigger a move. So the intermediate stop you can think of it as a pause. Okay, so the way this block works is you send it some set points and then the drive starts moving. Well, what if there's a reason for you to like hold up for a second and then like wait for something to pass and then continue on with the move? Well, that's what this intermediate stop is. It is kind of like a pause button. You say, hey, hold up on that for a second, and then, all right, go back to wherever you were, continue on. That's what this intermediate stop is. Both of those have to be 1 in order to move. You have to have them in order to move. So these next set points, we'll talk about. Yeah, so we're not going to talk about these other ones. So the next thing is the positioning type. Pretty sure that's going to be a 1 if you're doing a we might have to check that. Pretty sure that's a 1, but I may be wrong, and if I am, I'll update it. I'll update the description at least or something. So if you're watching this, be sure to check in the description to see if I've updated this with something. But so the selection, this next one is a selection of positive edge or continuous trigger. So what that means is, do you want, we haven't shown these analog signals, but you send like a position, velocity, acceleration, stuff like that. Do you want this to get updated only on a trigger? Actually, I'm lying. That's this. Oh, that's direction selection. So do you want your block to move in the positive direction to meet your set point, or do you want it to go in the shortest distance? That's basically what these values are. If both of them are on, then I believe that means that it is the shortest distance. If that's wrong, be sure to comment and correct me and yell at me. What I was talking about with the next thing is this little thing here is your actual set point acceptance edge. It's your trigger button. So you get all your set points set, you get everything going, and then bam, you tell the drive to go. You set the position, you set the velocity, you set your acceleration. Go. This little transfer type selection means, do you only want to transfer it on a positive edge? So here, a positive edge would mean that if it only triggers a new move here, right? Or if you were to kind of go and do this on that edge, each one of these would trigger a new move, whatever that move is. Even if this previous move was not done moving and you triggered a new move, it would override that if this was 0, like this, okay? If this is 1, you don't use an edge. Anytime that you update your position, it triggers a new move. And so that's what it's essentially, you can update, and anytime you update the position, then it's going to update the block. If you update the velocity in the middle of a move, it's going to update the velocity in the middle of a move. It's going to recalculate everything. So that's the difference between those. Now, let's take a peek at, let's click on this block for a second. And yeah, so these are just fixed set points. and then let's look at the analog signals. So pretty straightforward here. Wrong one. Sorry about that. These are pretty much straightforward. All of these are what you would kind of expect, okay? And MDI position, set point, velocity, set point, acceleration, deceleration, and then the mode is, so yeah. So those kind of what you would expect. That's kind of like our technology object stuff. And remember, all of these are in load units. So it's the resolution and all of that you set before. Let's talk about, though, this velocity override, because if you want to talk about one thing that'll mess you up quicker than anything is this velocity override. We talked about this in the technology object stuff. This is the same concept, that no matter if this this velocity set point, no matter if this velocity set point is set to a billion length units or load units per second, if this velocity override is set to 0%, thing's not going to move. It's just going to sit there and say, hey, I'm working. And we're going to look at the status signals here in a second. It's just going to sit there and say, hey, I'm working, but nothing's going to happen. So the first thing you need to do if you're troubleshooting this is make sure that your velocity override, your velocity equals 100%. Because that means that your velocity is 100% of your set point velocity. That's what that override is. Obviously, if it's 0, then it's going to run at 0% of your set point. But it's going to say that it's running, and it can get kind of annoying. So we're sitting at 2.5 hours, and this is kind of the basic overview of MDI. And I guess probably what I'm going to do next time is I'm going to talk about the SINA pause block specifically. Because if you want to dig into this MDI function, there's no better way of doing it than using the SINA pause block, because it kind of takes care of some of this stuff, like this, like mode adaptation. That's kind of important. And so some of the set points and things that we actually need, let's see, so MDI mode. So MDI mode means that you're going to set this block up this way. Clear this. The SINA pause block goes through and sets some of these signals to activate, because the electronic positioner has a couple of different other functions. It has jogging, it has this traversing blocks function, it has homing, and then it has the MDI block. MDI, though, is essentially you're moving in either relative mode, absolute mode, to a position according to acceleration and velocity. And you're going to set all of those set points. You're going to turn on MDI. You are going to turn on, so it's going to be 1 here. So you're going to be on here. You're going to need to have this. We're going to say positive, because think about, if you put a positive here, that means that if you have a negative position and you're doing like an absolute position, for example, that positive doesn't really matter. It's going to go to that absolute position. And then yeah, and so you're going to set this to 100, right? You're going to set this to your position set point. You're going to set this to, and remember, these are in load units. So velocity set point in load units per minute. And then this is acceleration and deceleration override. These are in percents. So let's just say 50%. And then, yeah, and you're good to go. Now, what you would do at that point would be, once you had all of these set up, you would then send over this. And so you would check that, and you would turn that set point acceptance edge on, and it would activate that move. And then it would take all these parameters, and it would speed up, run at a certain velocity, and then once it got to the position, it would stop. And then here's kind of all of the actual, if you're doing an absolute move, you have to have your reference point set. If it's in the middle of a move, then it's going to be either moving forward or backwards. The rest of these, if you were running an MDI move, it's going to be there. But yeah, these are pretty well straightforward kind of implementations of these. And so you can kind of see one of the things that you'll notice if, let's see, if you have that like you're actually moving, so an axis moves forward but then it's not moving. So like this. So I just had a question come across with like parameterize an encoder on starter. I don't believe so. Are you talking about setting up, like, if you have like a HTL encoder that's like a 1024 encoder, is that what you're talking about? And setting all the parameters up, setting all that up? Or are you talking about setting it up for positioning? Because I think I talk about setting up an encoder in one of my older live streams, and it would have been in starter. But that's probably one thing that I could probably show you real quick, because in this one, we're gonna have to call it encoder 2, because we set this drive up as a all right, hold on, this is an external encoder. Let me do this. Sorry, I'm doing something wrong. So let's go back in. So let's do this. I'm gonna go back in and reconfigure this. And so yeah, so because I selected this drive click right here, because I set this up as a drive click motor, it's expecting to pull that in. So let's go back and change this little selection here, and I'm just going to select a standard motor from the list. One TH8 random thing. Make sure that 9 amps. There. No. There. Just trying to make sure that there's not going to be a problem with that. That's fine. That's fine. No holding brake. So here is where in your actual, like, kind of the start of your what's it called, when you're initially setting it up, here is where you can set that up. This, for example, before was that drive click encoder. This is, you're now saying that it's going to come in with a signal module, and now what type of signal module will be based on what type of encoder you pick. So SM1, just means that it's going to come in with like either an SMC 20, SMC 30, SMC 40, something like that for this. And so we can either pick from our list here and say that we have like a 2048, a decent like Dynapar 2048 pulse encoder, and it's on the list. That's good there. And so that's a standard standard encoder from the list. You can also go and select, just enter the data and select that. Now, oh yeah. So this is where it can you get into the kind of more advanced configuration, because on this, your encoder, not only are you picking what type of connection that you're using on your SMC module, but you're also connecting the voltages. So here's where all of that encoder setup is on here. So like, let's say we had so like this is a 2048 with a R track with track monitor, bipolar. So that's like a AB type setup, HTL. So this would be, and then we'd pick that. Normally, most of your standard encoders are going to be on this other list. But if for some reason there's an issue, then here's where you can go in and put the stuff in. Now, I will say, let's go back in and cancel this, and let's just pick a standard 2048 HTL ABR. So like that's kind of what you would normally, a decent Dynapar encoder or whatever. We got all sorts of different options that you select there. Say, and we're calling that encoder 1. We're going to use that for our position control. We've done all this before. Siemens Telegram 111. Got everything. We're good to go there. So, cannot be wired or stored in the component box. So now, because that's coming in on a SMC module, we need to go to our topology, which is topology here, and we need to make sure that we have our encoder 1. We need to connect it to wherever it's actually the drive click cable, that cable from the top of our drive needs to connect over to the SMC module, and that's where you would connect that in. Now, one thing that I will go back to about like configuring the encoder, okay? This screen here is, if you go underneath your drive axis and configuration, pulls up this screen. You can click encoder data and it brings up that screen that we were kind of working with before. Now, here is something, there's this gear ratio, and there is a very rare instance to where you have some sort of gear ratio that is in between your encoder and your motor revolutions. So if for some reason the gear ratio or the encoder is like an external encoder, and it like your axis is here and your encoder is not physically one-to-one coupled to that, you would have to put this in here. And so the way I guess you would do this is you actually have to go in manually and do this. I don't know why it's not available on this right now, but that I'm just hovering over that, and so that's P432, that P433, and so have that plausibility check. We're gonna put it in at the terminal. Yeah, if you notice when I did that and I clicked on the encoder data, it changed my encoder number to free. So it kind of changed from that standard encoder from the list. It changed it to it's like selecting that other box. So let's take, what was that, 432? Let's open up our expert list real quick. Let's click over in this column. Let's type 432. Goes back to gearbox factor, and if we notice, so selected gearbox type, and P402 prevents the value from being changed. So we're just chasing through this. So P402, 1-to-1, and so, and then so there's different gearboxes. So like if you have some sort of gear ratio, like you have like a nylon gear wheel on like a pulley, something like that, here's where you change that, and that's in parameter 402. Now I will say I can change all of this stuff right now, because so say it's a 2-to-1 ratio like that. I can change all of this at will, free, because I am offline. If you're online with this, you would have to go first and change parameter 10 to encoder commissioning. Or nope. So you would change this to encoder commissioning, and then that would unlock the ability, that would like lock out the drive and say, hey, I'm changing stuff on the encoder, and then you could come back down here to like 402, change that, and then 432, and do that and change those ratios. So that's how you would adjust those values in Starter. Just out of reference, all of your 400 values in your expert list on a drive object, 400 values are encoder values. So all of your data is there, and if you're online and you want to start kind of changing this sort of stuff, again, and I'm clicking in this column and just typing 10, and it jumps to that parameter. So if you're online and the drive is there active, you will need to change parameter 10 to the value of 4, which is encoder commissioning. And then when you're done, you go back, make all your changes, go back and change this back to ready, 0, and hit enter, and it'll go back in. So hopefully that explains in parameterizing encoder. That's on an S120. G120 is pretty similar. Cool thing about all SINAMICS drives, if a parameter is shared between different drive models, the parameter number is the same. Like, so for example, the invert encoder app, like actual direction value, is parameter 410. And by the way, that is one of one of the things, especially if you're doing a like an induction motor and you're hooking up an HTL or TTL encoder onto something, this value, because what'll happen is you have two ways of getting things going in the wrong direction. If you have your two channels, your A and B channels, if they're flipped, then your encoder will think that it's pulsing in the opposite direction. That's with a pulse encoder. And if you, out of your 3 motor leads, if you have 2 of those swapped, then the motor will turn in the wrong direction. So you run into this situation when you're starting up what's called an induction motor with an encoder. You run into this situation to where first thing you want to do is try to get it to run. And the first thing you got to do is say, okay, is it running in the correct direction? And what you can actually get is, if you try to run it, you will get a motor blocked fault. And it doesn't make sense because at the end is necessary to, oh, absolutely. If yes, so copying RAM to ROM. So I did all this stuff offline. If you're doing it online, remember, if you're online, you are only looking at what is online. So my rule of thumb is if you make a change online and you've tested it and you like the way it works, copy RAM to ROM, then do an upload and then save. So copy RAM to ROM, if you were online, would be this button right here. Then an upload would be this button right here. So load drive unit to PG, because you have three different places. You have what's running on the drive, what's in ROM. So what's running on the drive, what's in ROM, and that's going to be loaded on the drive on startup. And then you have what's in your program. When you're working online, you are only working with this one memory location. And so if you went offline, your numbers would change because your project hasn't been updated because you never uploaded. If you turn it off, copy RAM to ROM, that stuff down on ROM never got updated with what was running. So yeah, so if you do that parameter 10, change your values and everything, you have to do a copy RAM to ROM, upload, save. And then that gets everything to where if you're offline and you make a change offline and you go and download, you don't overwrite what you just did online. That makes sense? Yeah, so we're talking about this parameter, or kind of this blocked fault. It doesn't make sense sometimes because the help file says motor blocked, speed controller at its limit, something like that. And what happens is when you're using encoder, it wants to move in a certain direction. And if it's moving in the opposite direction, it will say, oh, hey, I'm not moving in the right direction, so I need to be going in that direction. But it locks itself up. And so you'll get a motor blocked fault, even though nothing is wrong with that, all because your encoder, your two encoder leads are in the wrong place. And there's no real way for the SM module to know if you've got them hooked up right, or at least if you just have them put in the wrong place, it can't tell the difference. And so what you can do is, if you go to run your motor on an induction motor with a pulse encoder, like with an SM30 module or an SM20, I guess, you go to run it. If it runs backwards, you flip the leads, and you can either flip the leads, or there's a parameter in here that called direction rotation, and you can actually change the rotating order. But if it didn't fault out, that means that the encoder thought that it was running in the correct direction. So what'll happen is when you flip those leads, if it was running this way, now it's going to start running this way, and the encoder is all of a sudden going to think that you're running backwards because it thought you were running this way was positive before. So you can either go through and rewire the encoder, or you can go to this parameter 410 and change invert direction on both of them. So invert speed actual value and invert position actual value. You can change those to yeses. And in that situation where you have two sets of where you're where it doesn't want to run when it's running in the correct direction, it gives you that motor block fault, then that's where you do is parameter 410. And the reason I memorized that one is because one of the first projects that I ever worked on, that parameter caused us, it was 2 or 3 days of time, because we weren't expanding that box out there, and we were only changing this parameter. We weren't coming here and looking at this. There was another place where it had an invert signal, and we were only inverting for the speed. And so when we would run at the control panel, it would work totally fine. But then the second that we would go and try and do an MDI move, it faults out. It's a motor blocked. And because this uses the position controller, and for some reason, Siemens will allow you to separate them, that invert it for the speed, but don't invert it for the position. I don't know why. Like, again, one of those things, don't know why. But, yeah, so that's kind of one of those little things, that, yeah, just words of advice. And hopefully that kind of answers more about the encoder issues than you probably thought that wanted. But if it doesn't, just let me know, and I can make at least I might go back through and make another video just about setting up an external encoder, because there are a couple of things that you can do with this. Like I did before, I went through and started to add in an encoder, and you can separate out the motor encoder can be used for speed, and then you can have an external encoder that is on your actual process to use that as the position. And so that's where you actually have multiple indexes for these. So I'll show you real quick. Where is that? The best way to get to that. Mechanics. That'd be here. Yeah, there's a place where you, maybe it's in the setup, I believe, where there's one of the screens in the configure DDS that you're welcome for the explanation. I appreciate the feedback. But in the configure DDS, there's a place to where you can select the encoder that you want to use for the position control. And by default, you only have one encoder. It's on the motor, and that's what you use. If you have a situation to where you have an external encoder, like a linear encoder on a slide rail, like those are nice. You can set those up and use that for the position, and then you want really tight speed control on the motor, and so you use that for the speed control, because speed control is related to the actual motor speed. So yeah, you can do it that way. Or yeah, you can always separate out your motors or separate out your encoder, and yeah, use the position and the speed from that external encoder. They're infinitely configurable, put it that way. So we're hitting on 3 hours. These 2 hour streams have been getting longer and longer. And the thing about it is, like, today I felt like I didn't have as much, that I was like, I don't feel like I really have that much to talk about. We go for 3 hours. So, well, anyway, yeah, I appreciate everyone that has come in on this stream live, and if you're watching it on demand, again, I know I say this multiple times, thank you for finding it however you found it. If anything was helpful in here, please hit that like on the stream, and if you haven't subscribed, subscribe, so that if you're watching it on demand, you can get that notification if you ring the bell when I go live next time. I try to make this to where if you're in the US, that you can join in on your lunch break for most of you, and most of kind of European people and elsewhere in the world, I mean, if you're off of work, and I appreciate it. yeah, if you're off of work and you want to if you want to like come in and join in on this and kind of learn some more in your free time, yeah, hopefully there's an opportunity there. But yeah, so again, liking, subscribing, commenting, those are the ways to help this channel out as most, because we're trying to build a community here of automation engineers that will eventually be able to reach out no matter your background, your opportunity that you have to go to college, to school. Hopefully you're not restricted in what you have the opportunity to do. That's our goal here. And honestly, I thank you for joining, and always like keep learning, keep challenging yourself. But yeah, so yeah, it's awesome. Thank you for everybody that's coming. We'll join next time. Be sure to ring that bell. And yeah, we'll take it easy. See you later. Hey, what? You don't have to sneak. You don't have to sneak watching it. This is educational content. So that's one thing you're talking about. You don't have to sneak it at work. Like, invite your boss. He's like, hey, watch this guy. He can help out. He's gonna help us out. Anyway, talk to your boss next time. Get him online. Get them online. But anyway, talk to you later. See y'all later. Have a great weekend. Oh, absolutely. Take requests for future streams. Put it in a comment. Comment on the VOD, or just make it anytime. And yeah, I will come through and try to make a stream about it. Most of the stuff that we have done in the streams, honestly, have been about stuff that people have had questions on. A lot of these other videos, people will be like, hey, this was pretty helpful on this block, but how do you use this other block? And if I don't make an edited video about it, I'll at least bring it up on here so that the information's out there. So yeah, I'll always take requests. So I'm gonna go ahead and hop off now. If you have requests, hop on to the actual comments on the video on demand, and I will read those and reply back. Until then, y'all have a great weekend, and I'll see y'all next time. Bye.